Some cancers come back 10, even 20 years after a patient is declared cancer-free. For a long time, doctors couldn't fully explain why. Now we know, some cancer cells never actually died. They went to sleep. It sounds almost unbelievable. A cancer cell can deliberately shut itself down, sit motionless through chemotherapy, and quietly wait for years before waking back up. This isn't science fiction. It's a real, documented survival strategy called tumor dormancy. And it's the reason so many cancer treatments that look successful in the moment still fail years down the line. Chemotherapy drugs are built almost entirely around one assumption, that cancer cells are dividing. Dormant cells barely divide at all, which means the drugs designed to kill dividing cells simply have nothing to grab onto. So what actually flips a cancer cell into this sleep mode? The answer runs through a hidden signaling network involving stress hormones and a specific receptor inside the cell. And that network is exactly what this year's research targeted. This isn't a rare edge case either. Dormancy-linked relapse shows up across several major cancers, and non-small cell lung cancer, the exact type used in this year's study, is one of the most common forms worldwide. Picture two cancer cells side by side, one actively dividing and clearly visible to treatment, the other sitting still, quiet, and essentially untouchable. That contrast is the entire puzzle researchers have been trying to solve. So the real question driving this research wasn't how to kill cancer cells. It was how to wake them up first. And that's where a very unexpected tool enters the story: light. Let's slow down and understand the relapse riddle properly, because it explains why remission and cured are not actually the same word in medicine. A patient finishes chemo. Scans come back clear. Years pass. Life moves on. Then, without warning, cancer reappears, sometimes in the same organ, sometimes somewhere new entirely. Certain situations make this dormancy-driven relapse more likely, including hormone-sensitive cancers, incomplete surgical removal, and simply the passage of enough time for a dormant cell to eventually reactivate. Globally, this quiet risk touches an enormous number of people. Anyone counted as a long-term cancer survivor is, technically, also living with some residual chance that dormant cells are still present. For some hormone-driven cancers, the relapse risk doesn't peak right after treatment. It actually stays meaningfully elevated for well over a decade, which is unusual compared to most other diseases. Inside a treated tumor, it's rarely all or nothing. Even after successful treatment, a meaningful fraction of surviving cells can be sitting in this dormant, non-dividing state rather than being fully eliminated. The myth is that a clear scan means every cancer cell is gone. The fact is that a clear scan means no detectable tumor mass. It can't rule out a handful of dormant cells too few and too quiet to show up. That gap between no detectable tumor and truly zero cancer cells is exactly the gap that this year's research set out to close, starting by finding what actually controls the sleep switch. The molecule at the center of this entire story is called the glucocorticoid receptor. It's not exotic or rare. It's actually a completely ordinary stress hormone sensor that every cell in your body carries. Normally, this receptor does genuinely helpful work. It helps calm inflammation and helps regulate your immune system's response to stress throughout the entire body. The glucocorticoid receptor sits inside the cell, waiting. When it detects a stress hormone circulating in the blood, it changes shape and becomes active. In certain cancers, including some forms of lung cancer, this same activated receptor sends a very different signal. It tells the tumor cell to essentially stop dividing and enter a protected, dormant state. In other words, the tumor is hijacking a completely normal stress response pathway and repurposing it as a survival bunker, one that most cancer drugs simply cannot reach. That contrast is stark. An actively signaling receptor barely slows a healthy cell down, but the same signal inside a susceptible cancer cell can drop its division rate almost to zero. So why not just destroy this receptor everywhere and be done with it? Because it's essential elsewhere in the body. Remove it completely, and you'd cripple inflammation control and immune regulation across every organ. That's the exact wall researchers hit. The receptor is essential everywhere, but the problem is only local, inside the tumor. Solving that mismatch is what the rest of this story is about. What if you could disable this receptor only inside the tumor and leave every other copy of it in the body completely untouched? That's the question the ETH Zurich team set out to answer. The trade-off was clear on paper. Destroy the receptor everywhere and cause serious systemic harm, or leave it alone everywhere and let dormancy keep protecting cancer cells indefinitely. Their solution borrows a recycling system your cells already use naturally, a way of tagging broken or unwanted proteins with a tiny molecular label that marks them for disposal. The engineered switch has 3 parts. One end grabs onto the receptor, a flexible middle piece connects everything, and the other end grabs the enzyme that attaches the disposal tag. Here's the elegant part. Under normal light, the connector stays straight, holding both ends at exactly the right distance to tag the receptor. Under a specific wavelength of light, the connector kinks, throwing off that distance, so tagging simply can't happen. Quick pause. If this breakdown is helping you, take a second to hit like and subscribe. It genuinely takes a lot of effort to make videos like this, and your support keeps them coming. This isn't a vague, dimmer-style effect either. The switch responds to specific, distinct wavelengths. One color of light turns tagging on, a different one turns it off. In practice, the plan is to inject the switch directly into the tumor, then shine light on the surrounding healthy margin to disable tagging there, leaving the tumor core as the only place the receptor actually gets destroyed. This class of light-controlled disposal tags has a name: photoproteases, short for photoswitchable proteolysis targeting chimeras. It's a mouthful, but the idea underneath it is beautifully simple. Light as an off switch for side effects. Elegant engineering means nothing if it doesn't work in a real, living cell. So the team took their switch out of the design phase and into the lab. They tested it on A549 cells, a well-established laboratory model of human non-small cell lung cancer, chosen specifically because this cancer type is known to rely on the glucocorticoid receptor for dormancy. When the active form of the switch was applied, the receptor broke down rapidly inside those cells. And when researchers checked which genes had switched back on afterward, the pattern matched exactly what you'd expect from cells waking out of dormancy. Crucially, the inactive form of the switch, the one meant to mimic light-off conditions, behaved as a neutral control. It had no measurable effect on those same genes. That contrast is what proves the switch is actually doing the work. Out of multiple connector designs the chemistry team built, 2 showed exactly the desired light switching behavior, cleanly flipping between the tagging and non-tagging states on command. The bigger picture matters here too. Cells woken from dormancy are, in principle, far more exposed to standard cancer drugs than cells that stayed asleep, which is the entire point of doing this in the first place. So what did this round of lab testing actually confirm? 3 things. The switch destroys the receptor. That destruction is controllable by light, and the destruction genuinely wakes the cells up. That's a genuinely strong result for a lab dish. But a lab dish is not a body, and the researchers themselves are the first to say the next step has to be testing this in a living organism. Every promising cancer discovery eventually has to answer the same hard question: how far is this from actually helping a real patient? For this one, the honest answer is early, but with a real path forward. The single biggest physical hurdle is light itself. Light only reliably penetrates a few millimeters into human tissue, which limits exactly where and how this technique can currently be delivered. For a lung tumor, this limitation is manageable. An endoscope can deliver light directly to the tumor's surface from inside the airway. For tumors buried deep in the body, that same approach doesn't work nearly as well. That's exactly why the team is already working on a next-generation version tuned to near-infrared light, a wavelength that penetrates far deeper into tissue while remaining gentle on healthy cells. The team also designed this system to be modular, meaning the same switch mechanism could, in theory, be redirected at other hormone receptors, including ones implicated in hormone-driven breast cancer and advanced prostate cancer. Weighing it honestly, the upside is a genuinely novel, reversible, tissue-specific way to disarm cancer's hiding strategy. The downside is that it's still lab-stage science with real physics and safety hurdles left to clear. Looking at the realistic timeline for any lab discovery like this, moving from a validated cell culture result to an approved treatment typically takes well over a decade, even under a best-case scenario. The myth would be calling this a cancer cure available today. The fact is it's an early but genuinely promising proof of concept, real progress, honestly framed. Let's zoom back out. Why should any of this matter to someone who isn't a cancer researcher? Because it reframes one of the most frightening ideas in oncology, the unpredictable, seemingly random relapse. This research is a laboratory result, not a treatment you or a loved one can access today. It's important to hold both the excitement and the caveats at the same time. Here's the whole cycle in one breath. Stress hormones activate a receptor. That receptor pushes some cancer cells into a hidden dormant state, and a light-control molecular tag can now selectively destroy that receptor to reverse the process, precisely and only where light reaches. Compared to older, non-targeted attempts to block this receptor, the light switch approach trades a body-wide effect for a precisely localized one, which is the whole reason it's considered such a meaningful step forward. What you're taking away from this video: dormancy is real. It's a major reason relapse happens, and for the first time, researchers have a tool that could wake and re-expose these hidden cells with real precision. Quick recap before we go. What triggers dormancy, what the switch actually does, and why light matters so much to the whole design. One last check: which part of the switch is actually turned off by light exposure? This video was built on the original PNAS study published in May 2026 and ETH Zurich's own reporting on the work. Links and full citations are below if you want to go deeper. Thanks so much for watching. If this helped, like the video and subscribe for more clear, simple explainers. And I'll see you in the next one.